Okay, fun problem. Lots of math with J's. The overall concept here is that the impedance is a function of the angular frequency. Okay? So here's our circuit. There's an inductor and a resistor in parallel. And then there's a resistor and a cap tacked on in series after that. So this is a 20 ohm. This is a 5 millihenry inductor. This is a 5 ohm resistor. This is a 25 microfarad cap. We want to find the equivalent impedance of this whole thing for omega is 2000 radians per second. And then we want to solve it again. The equivalent impedance for all of this stuff for omega is 8,000 radians per second. So, the impedance Z is a function of the frequency, right? We're going to solve for the impedance at two different frequencies, we get two different values. So that's the basic idea here. And what you'll find is one of these is going to be more capacitive, and then this one's going to be overall more inductive. So that means it's changing. As we change the frequency from 2000 to 8000, it's going to change from a capacitive overall to an inductive overall. That means it's going to pass zero, right? It's going to pass a point where it's purely resistive, right? Neither inductive or capacitive, but purely resistive. So that's the third thing they're asking. What is W for a purely resistive circuit? Right? So let me just say that one more time. So this whole thing right here, when you apply a signal that has a 2000 radians per second frequency, it's going to have an overall capacitive tendency. And then as this frequency speeds up, it'll the capacitive component of that will drop until it becomes purely resistive. And then as the frequency goes up even more, it'll become inductive. So, and we're going to solve for all three of those cases. So part A, the impedance of this inductor right here is just J omega L. It's J 2000, 5 millihenries. It's J 10 ohms. The impedance of the capacitor is -1 over J omega C. It's going to be -1 over J omega is 2000 radians per second, 25 microfarad. It's going to be -J 20 ohms. All right, now impedance simplification. I'm going to call this equation 1. The Z equivalent is these two guys are in parallel. So our formula for parallel is the product over the sum. So the impedance of the 20 ohm resistor times the impedance of the inductor, right? The product of these two over the sum of those two things. Okay, that's the parallel equivalent of this thing. And then the parallel equivalent of this thing is in turn in series with the other two things. So we just add them on there. So this is Z5 plus C of the cap. So that is the impedance of the resistor. The 20 ohm resistor is just 20. It's just a scalar. And then Z sub L is J10, right? And then their sum at the bottom is 20 plus J10. And then the impedance of the 5 ohm resistor is just 5. And the impedance of the 25 microfarad cap is just negative J20. So work all this out in your calculator, right? Calc. And you get 9 minus J12 ohms. So this is the resistive component. You know, it's a resistive, it's scalar, and this is the reactive. You know, it's a you know, has J in it. It's imaginary. And the overall, this thing has a real component of 9 and a imaginary component of 12, minus 12, going, so it's going down. It's like this. It's overall capacitive. It's you know, the current's going to lead the voltage, and it's the angle's negative. The J component is negative. So is that an answer? Yeah, that's the answer. This is part A. This is the Z equivalent for a frequency of 2000. Just wanted to point out that it has a resistive component, a reactive component, and it's overall ice. Okay, if we do part B, and I'm not going to actually do it because it's similar to A, but you know, with omega equal to 8,000, what you're gonna get is you're gonna get something that's overall inductive. It's going to have a positive angle. The J component is going to be up, you know, positive, and it'll have a resistive component as well. But you can work that out. You know, I'll probably ask you to do that on the homework, but it's going to be inductive. So somewhere in between 2000 and 8,000, this thing went from capacitive to inductive. And you know, at what frequency does it become purely resistance? At what frequency does the impedance of the cap cancel the impedance of the inductor in here, right? So so part C is asking, what is omega? What is the frequency for a purely resistive circuit? We'll use this equation 1 up here and do some fancy stuff to it. So Z equivalent is 20. So we can just leave the resistance in there because it's not hurting anything. But we need these. We'll leave the Z sub C and Z sub L components as expressions because we're gonna solve for omega. Now we could put L in there. You know, we know L's not changing. It's still going to be 5 millihenry, and C is going to be a 25 microfarad. We could put those numbers in there, but it just makes the algebra harder to have, you know, the value of L in here and the value of C. So L and C are known, okay, but we're not going to put the numbers in there. And omega is the unknown, okay. So this is an R value, this 5. The 20 is an R value, you know. It's okay. The 20 and the 5 are okay. What we need to get rid of is we need to get rid of the J's. So we have to get rid of J's. Because that's the, you know, these, the J components have indicated in a reactance, right? We don't want any reactance. We want just resistance. So we need to get rid of the J's. So the way to do that is to get the terms with J's in them to cancel. So let's see how to say that. We need to get we need to get the j's on the top. Having the j on the bottom is a problem. We need to get the j's on the top, then find when the j terms cancel. Okay, so let's multiply top and bottom by the complex conjugate of the denominator. That little trick. So take the denominator here, multiply the top and the bottom times the complex conjugate of that, and it'll get rid of the j's on the bottom. So so just taking this term right here, because we can deal with this term. If we just had a j, so we have a term with j's here and we have a term with j's here. If we just had a j just on the top, then we could get these two terms with j's in them to cancel. So we need to get just j's on top. So the trick there is take this term here. So it's going to be 20 times j omega L over 20 plus j omega L and multiply it times the complex conjugate of the denominator. So 20 plus j omega L, the complex conjugate of that is 20 minus j omega L. So multiply the top and the bottom times 20 minus j omega L. Okay, and if you do that, then let's see, 20 times 20 is 400 j omega L. And this minus j omega L times j omega L, the j's cancel. The j's become minus 1, which turns this negative into positive. So you end up with plus, what are we doing here? J omega L times the 20 just comes across, and then omega squared L squared. And the j times j becomes minus 1, and you get a positive sign here. And then multiplying the bottom, you get 20 times 20 is 400. And 20 times this j omega L will cancel 20 times minus j omega L, so those will go away. And then these two guys here, once again, the j times j is minus 1, so you'll get a plus, and you'll get omega squared L squared. Okay, so bringing down these the other two terms, the 5, so plus 5 minus j 1 over omega c. Okay, ran out of room, so let's break this up, these two things. So this equals 400 j omega L over 400 plus omega squared L squared, plus this other term was 20 omega squared L squared over 400 plus omega squared L squared, and then plus 5 minus j 1 over omega c. All right, this is an r. That's okay. This has no j in it. It's just resistive. So this term's resistive, and this is all resistive because it's just a number. There's no j in there. It seems L has funny units and R is radians per second, but if you do all the units cancel, you'll get ohms. It's just plain ohms and no J. So this resistive and resistive, that's okay. This is okay, but we want these two terms to cancel. So basically, this will be purely resistive when the J terms cancel. Or, in other words, when 400 j omega L over 400 plus omega squared L squared, this thing here is equal to j over 1 omega c. When these two terms are equal, then it's kind of like you're saying how to say that? I'm not sure how to say that, but when these are equal, they'll just yeah, they'll just totally drop out, and you'll just have this this resistance here. So so basically, just to be totally verbose about this, J terms cancel when 400 omega L, just canceling erasing the J, basically is 400 plus omega squared L squared equals 1 over omega C. Okay, when those two terms are the same, then these will just gone out, and you'll just have, this will be the resistance of the equivalent circuit here. That is to say, this circuit will be purely resistive. Yeah. So solve for omega. So let's see. So move the omega C over to the other side, 400 omega L, and move the denominator over here, 400 plus omega squared L squared. And then multiply the omega C in, you get 400 omega squared LC. Once again, L and C are known, but 400 plus omega squared L squared. Then bring the omega squared L squared over here, and trying to solve for omega. That's what we're trying to do. So so we can pull out the omega squared out of this sucker's 400 LC minus L squared over 400. And so yeah, so this guy is going to be root of all this stuff, 400 LC minus L squared. It's going to be yeah, then we know, plug the values in, and you're going to get 4,000 radians per second. Okay, which is right in between 2,000 and 8,000, right? As it changed from initially tending towards capacitance, and then the frequency increased and it went to inductance. It passed through 4,000 where it became purely resistance. So that's part. And then yeah, I missed part D. What is that? Z equivalent. For purely resistive. What is it? It's so Z equivalent at 4,000, right? It's here, solve it one more time at 4,000, right? Just make this 4,000, and you'll see that the J terms are going to cancel, and you just get 15 ohms. You just plug into, it was via plug into equation 1.